Hello friends, Namaste and Jai Hind. Welcome to Dr. Ganesha's Signal Processing, Computer Vision and Artificial Intelligence lecture series. This is a first lecture on mathematical models which are used in this various subject, which will help to understand these subjects in a very simple way. The first mathematical model is impulse function. So we'll start with what is an impulse function. Basically, impulse function is a ideal abstract function which has pulse width of 0 and amplitude infinity, and mathematically it is represented as f of x is equal to delta x. Pictorially, one can visualize this function on xy plane in the following fashion. So you can see the orange color bar with amplitude infinity and pulse width is 0. Now, what is the exact use of this function in various subjects? So basically, I would say it forms a mathematical foundation for simulating various signals, and it has some peculiarities which we'll see at the end of the lecture. Now, first, try to understand the mathematical aspect, and then we'll see conceptual part along with physical interpretation. So this is a mathematical representation of impulse function, which is having pulse width 0 and amplitude infinity located at value of x equal to 0. Now, if it is a shifted, how it will look like? Here, just I'm changing a variable x from t. X can be time, frequency, or any other variable. So here, since we are talking about signal systems, computer vision, machine learning, signal processing, I am using a variable t as a time. So if it is shifted in time domain by amount, say t naught, then how it will look like? So it is so simple. It will get shifted to t naught, and the minus sign indicates it is shifted on the right hand side. If this would have been plus sign, it would have shifted on the left hand side, that is at position minus t naught. How one can understand this? So the simple process is equate argument t minus t naught equal to 0, and then you will get a position of t, that is a t is equal to t naught. Now, similarly, one can visualize function in another variable space. Here, it is a frequency domain. So in frequency domain, if it is shifted by amount omega naught, then you will get a same function at position w, which is the angular frequency equal to omega naught. Now, we'll see some peculiarities or characteristics of impulse function, and one of the important characteristics is area of the impulse function. This understanding will help you to solve many mathematical problems. So first, we'll see how to calculate area under the impulse function. It is slightly difficult because its amplitude is infinite and pulse width is 0. So how one can model? Now here, don't try to grasp everything. Try to understand or visualize the system, which is very important. That will make you to think. Don't try to by heart. So here, we can visualize a short duration pulse of width tau and amplitude 1 by tau. So this is a very elegant way of representing direct delta function or impulse function. Now, when you make tau 0, then automatically 1 by tau will become infinite. So we can define impulse function with the help of a rectangular pulse under limiting case such that the pulse width tends to 0. And once one can visualize, when pulse width becomes very small, the amplitude will become infinite and it will converge to a function known as impulse function. Here, one can calculate area under any function with the help of integration process. So when you integrate any function f of x, you will get an area under the f of x. So here, our f of x is delta t, and this is a standard relation for computing area under the function. So we'll apply to impulse function. Now, we cannot solve this equation because the delta t definition, original definition, is very abstract. So we'll use the modeling definition with the help of rectangular pulse. So we can substitute that and we'll find the second equation. Now, limit is with respect to tau, while integration is with respect to time. These are two independent variables. So one can change the order of operations. So here limit is done first and then integration. Since they are independent, you can change order of this limit and integration operation in this fashion. Now, what is a p tau of t? So here p tau of t is nothing but the magnitude is 1 by tau and width is tau. So if you calculate the overall integration of p tau by t is an area under p tau by t, and that can be computed with the help of simple formula height into width. So height is 1 by tau, width is tau, and if you solve this, you'll get 1. So it shows the area under the impulse function is 1. Now, one can think about area using direct delta function, then it is very difficult. But if you model using rectangular impulse function, then it solves the problem. And both are same. So here, now we'll see when you multiply an impulse function with any other function, say f of t into delta t. So these are simple mathematical process which will be used in the analysis of various signals and systems and signal processing and many other subjects. So let's understand the simple operations. So when you multiply a function with delta t, so it's quite obvious. One can see pictorially the impulse function multiplied with any arbitrary function f of t will exist only at t equal to 0, and rest of the area or rest of the values of x or t, it will be 0, and therefore the product will become f of t into delta t is equal to f of 0 into delta t. Now if you integrate this function, so previous one was a multiplication process, now second one is if you multiply and integrate, then what will happen? So you can substitute the previous relation in this expression and you'll find it is simplified to f of 0 integration of delta t, and we already know the answer, it is 1. So you'll get f of 0. So try to understand here important steps. When you multiply impulse function with any arbitrary function, the product will exist only at 0, but impulse function will be still present in the equation. When you integrate it, it will become f of 0. Now, what is the exact application of impulse function? There are many applications, but one of the typical application in signal systems and signal processing is a sampling function. So here, a sampling function can be implemented with the help of repeating the pulses, which is called train of impulses. So one can see here, this is the train of impulses at uniform interval t, capital T. Now this sampling function simulates behavior of sampling of analog signal, which is used in the process of analog to digital conversion. We'll see that analog to digital conversion in our upcoming lecture series. At this point of time, try to understand what is a sampling function. Now, sampling function is nothing but a periodic version of impulse function. This function, if it is multiplied with any unknown function, you will get a sampled version of that function or that signal. Now here, this is a foundation signal in digital signal processing subject, where we capture analog signals and then we sampled it, converted into digital signal, and then process using computer, and it evolves into a separate subject which is called digital signal processing. So here this is what about impulse function in short, and we'll see in upcoming lecture the new model called exponential function, which is very, very important. Now before we stop this lecture, what is the exact use of impulse function? We will see in our upcoming lecture, but here I can highlight certain points. The first one is impulse function. If you see the Fourier transform, it has all the frequency. It is a flat function. It is 1, so that it can be used in modeling any generic function because it has all the frequencies. Second one is when you apply impulse to any linear time invariant system, the output response is called impulse response, and that represents transfer function of the system. One of the application we already saw, which is a sampling of analog signals coming from various sensors, which is converted into a digital signal in order to process using computer. So thank you very much for this first lecture in mathematical model. I hope you enjoyed it.